So our next unit is called Triangle Inequalities. And here the objective is to use inequalities to describe the relationships among side lengths and angle measures in a triangle. And we start with some simple questions. Is it possible to form a triangle with the 3-inch length, 4-inch length, and 5-inch length? Okay, yes. We'll talk about why in a moment. 2. Is it possible to form a triangle with the 3-inch length, 4-inch length, and 8-inch length? No. We'll talk about why in a moment. And finally, is it possible to form a triangle with a 3-inch length, 4-inch length, and 7-inch length? The answer again is no. So, how did I know these things? And what would make it impossible to form a triangle given a bunch of side lengths? Well, let's take a look at some of the fundamental properties of the side lengths of triangles. Here we have a triangle, and let's call the side lengths A, B, and C. There's something called triangle inequality. Or actually, it really should be triangle inequalities, which states that if you take any two sides of a triangle, let's start with A and B, and you add them together, the sum of the lengths of those two sides must be greater than the length of the third side. So in this triangle, we know that A plus B must be greater than C. Let's take two other sides, A and C. A plus C also must be greater than B. And finally, if we take B and C as sides, we know that B plus C must be greater than A. Well, okay, those don't seem like they're difficult to remember, but why? Why is it true that the sum of two lengths of a triangle has to be greater than the third length? Well, let's take the second triangle as a good example. Let's try to create a triangle with the lengths 3-inch, 4-inch, and 8-inch. You'll see that this triangle does not meet the triangle inequalities. First of all, let's pretend we could draw a triangle. And so let's draw a pretend triangle with 3 inches, 4 inches, and 8 inches. And let's see if each of the three sides meets the triangle inequalities. Well, 4 plus 3 is 7. Is that greater than the remaining side 8? No. Okay, so we already know this triangle is impossible because it does not meet this triangle inequality. Well, let's try the other triangle inequalities. Why don't we pull these two sides? 3 plus 8. Is that greater than the remaining side 4? Yes. How about 4 plus 8? Is that greater than the remaining side 3? Yes. But still, we have one triangle inequality that is not fulfilled, and therefore this triangle is impossible. It cannot exist. And now let me show you why. Let's draw this, in fact, to scale, and let's use the centimeters. And let's try to make one of the sides 8 centimeters. I'll make that the one on the bottom. And let's make the other two sides 4 centimeters and 3 centimeters. Let this side be 4 centimeters, and let this side be 3 centimeters. Okay, now this is our to scale version, 8, 4, and 3. Take a look at this triangle. What do you think the problem is? Okay, if you thought that the problem is these two sides can never join each other to meet in a vertex, you got it. Okay, these sides are too short. There's this gap between them, and no matter what we do, no matter where we move these sides, we can move them down like this. We can move this side down like this. However we move them, they will never meet. They're too short. Sides are too short. And that's because 3 plus 4 is only 7, which is less than 8. So they can never reach each other. And that's the thing about the triangle inequality. It ensures that the sides can all meet each other in a vertex. So let's confirm that 1 is possible. We just said it was. 3, 4, and 5 inch length. Well, let's try every combination of sides. Let me draw 3, 4, 5. Again, it might be a make-believe triangle. We don't know. Let's try 3 plus 4. Is that greater than 5? Check. Let's try 3 plus 5. Is that greater than 4? Check. Let's try 4 plus 5. Is that greater than 3? Check. They all work. So this triangle does exist, and it can exist. Let's take a look at the very last triangle. I said, no, this triangle cannot be. 3, 4, and 7. Well, let's again draw our imaginary triangle 3, 4, and 7, and let's check all the inequalities. Remember, we're going to do this like we did for a triangle. Let's call this triangle ABC. A general triangle, let's again list out the inequalities for a general triangle. We have A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A. Okay, so now let's try each of those corresponding inequalities on this triangle. A plus B would be 3 plus 4. Is that greater than 7? No. 3 plus 4 equals 7, but it's not greater than 7. So we already know this triangle is impossible. Well, let's just check the other ones to be sure. A plus to see if the other ones are possible, if the other combinations are possible. 3 plus 7 is greater than 4, yes, and 4 plus 7 is greater than 3. Yes, they're all true. The only one that isn't true is 3 plus 4 is greater than 7. The thing with the triangle inequalities is this. If you find even one inequality that doesn't work, then you know the triangle is not possible. So in this case, what happens is, if we draw this triangle to scale, let's draw 3, 4, and 7 sides. So we have one side here that is 7 centimeters. I have one side here that is 3 centimeters. And then I have one side over here that I'll make 4 centimeters. Okay, so this is 3, 4, and 7. We have very similar problem with one slight difference. These two sides will eventually touch each other, but only if they are lying right on top of the 7 side. So in other words, if I fold 3 all the way down to here so that it's touching this, I can also fold the 4 all the way down to here, so it is also touching. So they will meet, but they will meet when they are flat on top of the side of 7. And that makes sense because 3 plus 4 is equal to 7. So when they both come down, they meet right here, and the 3 side is there, and the 4 side is there. But that's not a triangle. That's basically a straight line. A triangle has to have some area, and there's no area there. So they can't equal. They must be greater than the third side. And therefore, these last two triangles are not possible. Well, checking 3 inequalities each time is a bit much work, right? Is there a shortcut? Is there some way that we can only maybe check one of the 3 inequalities to see if it doesn't work? Well, notice that in all the cases we looked at, the inequality was always wrong when we looked at the 2 smallest sides being added together. So with the 3, 4, 8 triangle, it was the smallest sides, 3 plus 4, not greater than 8. And here, it was the smallest side, again, 3 plus 4. In fact, it will generally turn out that the only side you're going to have to check, or the only 2 sides you're going to have to check, are the 2 smaller sides. And you're going to have to see if the sum of those 2 smaller sides is greater than the largest side. So that is the shortcut in the triangle inequality.